Okay. So, by the way, we've got a lot of actual stuff to fill in here, but the sections I'm now working on, one is counting the eames of mathematics and physics.
Yeah.
Okay.
Yeah.
And then I want to talk a little bit about implications for the future of mathematics.
Okay. Great.
Okay, let's talk about, let me just make a file here. And let's see if we are in 2022. My God, 2022 is empty.
Yeah.
Did I manage to make a thing for, I mean, we're not causally related to whatever, I don't know. Did I manage to make one? Did I manage to put? Okay, so we're at 58, mathematics 58. Okay, so what I'm saying here is how many eames observers like us sample only tiny pieces of the Rulliad in doing both physics and math. How many eames do they contain? How many eames do we conflate together when we make coarse-grained measurements? How big are we as observers when measured in eames? So another question would be, how big is basically, is the light cone? Well, you see, this is where I get confused. Is the past light cone for...
Do you mean emulation cone?
Well, I mean the past, yes, I mean the past
Sorry.
generalized light cone, entailment cone.
Entailment cone. What did I say? Emulation cone. What the heck
You
is
said
that?
emulation, entailment cone. For both physics and math. Okay, that's one question. Another question is how big is our sort of conflation zone? Okay, so our conflation zone in physics. Okay, so in the end, in physics, let's just take these as in physics. So let's take the case of physics. So our conflation zone is about 1 cubic meter in, let's say, in a first approximation. No, maybe not a cubic meter. Let's say, I don't know, how big is the region that we conflate in space? You know, let's say a micron or something. I don't know. You know, we're not typically measuring space at a level. This is where it gets complicated to say what we're talking about, but it's of order, you know, for space. Well, the conflation zone is certainly more than 10 to the minus 20 meters. Much, because that's the limit on the granularity of space. And in reality, the everyday limit on the size of space that we distinguish is probably, I don't know, a micron or something, let's say. Is this making any sense, what I'm talking about?
Where do you get the 10 to the power of negative 21 from?
I know that. That's a factoid about what's been, that's the furthest we've been able to probe with particle accelerators for smallness of effects, for smallness of granularity of space.
Okay.
Just a random factoid. Okay.
And what about the micron?
Well,
I
how
mean,
big
I know it seems reasonable, but I'm just inquiring into your intuition.
Well, I mean, that's it's just what would we every day distinguish as not, you know, if you were told space is granular and you know, that's, you know, it's smaller than a pixel.
Yes.
If you were told space is granular, then, and it's, you know, you could, and it's 100th of the size of a pixel, and you say, okay, might be true. I mean, you kind of know that it's Well, I mean, okay. I mean, this is kind of weird. I mean, it's kind of weird what we're saying here, but this is, it's a practical matter. Like, that's our everyday, I don't know. I mean,
You just mean as observers without any instrumentation.
yes.
Yeah. And besides like seeing eyeglasses or something. Yeah.
Yeah, right. Branch Hill space, we don't know. I mean,
Have you seen this news that science has been able to entangle a tardigrade?
oh God.
Oh, it's not really entanglement, but just a fun one.
Yes, it is a fun one. Especially after our friend Nova Spivak managed to put tardigrades on the moon.
Yeah.
We could entangle those. Yes, I don't think we really have any idea for branch Hill space. But okay, so let's look at the math case.
Okay. Mm-hmm.
So the conflation zone is, okay, so basically the question is, how big is the Pythagorean theorem? I mean, that's the first question is, so that's the thing that we talk about, right? So we talk about, okay, here we're basically asking, you know, what are human scale coordinates for space? This is a little different because I mean, what we're saying is, let's say 1 micron is made up of, you know, a 1 micron cube might be, I don't know what it is, it's 10 to the minus 2093 cubed. It's let's see, 93 times 3 divided by 93 over 6. I mean, it's 93 cubed over 6 cubed. 93 times 3 over 6 times 3, which the 3's cancel, surprisingly enough. Something's wrong with this calculation. 10 to the minus 93 meters. How many 10 to the minus 93 meter cubes are there in a cubic micron? I guess it doesn't matter which that it's cubic because it's the same. Okay, so anyway, that's actually oh, that's why I'm getting the wrong answer. Absolutely stupid answer. Okay, that's more like it. That's more like it. What am I doing? You guys are, so that means that
Yeah.
that means in 1 cubic micron, ten to the 260 atoms of space. Okay, so that is the scale of one kind of what we think of as being just one place in space in some sense.
Okay.
So is this the analog of that? You know, the Pythagorean theorem is.
Now, Nick, can we get some sort of size estimate for the Pythagorean theorem from the MetaMath language?
We can. We already know that. We already did that for the Euclid post. Okay. So I mean, maybe Nick can give us a better one. So what I got here, and I'm going to ask about the definitions part of this. So
From the MetaMath library.
Mm-hmm.
Yeah.
I don't know. Well,
I think we've got here. Go ahead.
Oh, I just mean it's possible to extract it. It's not going to be big. I'm not sure whether it's like.
Well, this is the claim here. The full graph is 7,000. Okay. But, okay, so that's saying that it has 7,000 elements. But how many of those are definitions? And what does this mean in terms of unwinding of the proof and so on? This is an accumulative result, right? That's the cumulative derivation, correct?
Yeah.
And what does it mean? What do the definitions mean in here? Are they relevant to this, or do they mean that we've actually got more stuff in here? I think this is
Nick, definitions in MetaMath.
Definitions in MetaMath is just, it's like code grading.
Yes.
It's just
okay,
Yeah, that's right. So that answers Stephen's question.
Well, right, but then what I want to know is how many actual eames are there? How many actual elements of the see the question is, okay, so here's my question.
So we basically have to unpack the
Compile.
definition.
Yeah, what is the compilation?
Fine.
You know, what does the Pythagorean theorem compile to? Now that must be knowable because the proof of it must generate that symbolic structure. So can we run it, for example, and just generate that symbolic structure?
For MetaMath, you can.
Yeah, well, can we just do it? What do we do?
Yeah, just try to remember how it's called in the MetaMath. I'm gonna do it just a little bit.
Okay. But so what you're about to generate is the length of the Pythagorean theorem in raw. So, okay, what we need it in terms of, what am I saying? In terms of the primitives in which the axioms are stated. Right?
Yeah. Variables and what else? And constants, variables and constants.
And function names, presumably. But there won't be very many of those. We've got to have removed all the other definitions. We don't want any fancy functions. Okay, so then the next question is, how big is the quotes most difficult theorem in MetaMath? And actually, there's this guy, let me just look him up. Okay, this guy, Freck. The top 100 theorems.
According to what ranking criterion?
Oh, who knows? The irrationality of the square root of 3. So let's square root of 2. There we go.
No, Pythagoras is number 4. Norman McGill.
No, but that's the steps in the proof.
Yeah, I know.
So the question is, what does it compile into?
I know.
Yeah, I can't expand the Pythagorean fully, like to the just the IMS basically of the MetaMath.
Because it's too
giant.
big.
Yeah, it seems so. Yeah.
Okay, so
Even
roughly,
even if you don't expand it, you have a tree. Like how many nodes? Three leaves. And I know almost 1,000 nodes, and each of those can be expanded further and further.
okay, so can we look at what? Okay, so in this case, how do I figure out what these numbers here? What do those numbers mean? Or are they just node names?
Just an index, some kind of.
Okay.
Position in the library, maybe.
Okay. Depends on, but there are a lot of axioms here. How come it's got so many axioms?
Axiom of existence. Or how many? It should be as many there in the ZFC. Right?
Well, there's a lot more here than in ZFC.
Maybe there's some I don't know, trivial ones, like maybe some versions.
But look, it's got axioms for the reals. Okay, so here, wait a minute, what is this one? This is square root. Let me do the one for Pythagorean.
Basically definitions then, right?
Okay, so here are the axioms for the Pythagorean theorem. Okay, so first question is what axioms were actually used here, including things like, the hell is this? I mean, this is some. Not x equals y implies y equals z. For all x, y equals z. The axiom is logically redundant. Okay, so the basic point here is that it is nominally proved from. Is there a scrapable version of this page, or do you have the thing? Can I use your code to import this somehow?
Yeah, yeah, sure.
What is it called? MetaMath.
It's a MetaMath proof and not ready functions.
Oh, it's not MetaMath import. It's
No,
not
MetaMath import is just
I'm sorry?
MetaMath import just a raw data.
Okay, but that might be enough for what I need.
Maybe. No, it's not. It's not going to work like that. You have to import. No, it's not going to work. You have to import the whole library, like setmm, and then you ask for this theorem in there.
Okay, so I say here setmm.
Now I have to use the link. Just it's in my MetaMath proof notebook.
Okay.
Function there. I have just the first example. It just imports the setmm. And right now I have a tree of Pythagoras of this theorem that you're looking at in there.
Where is it?
Non-ready.
Okay.
Function repository sources.
I can. So where should I go? Should I?
It's just the first line. Like first code.
And
there. Mm import equals. So first you just import the whole library. That can take a while. And then make a tree.
Okay, so this is the leaves of the tree, but then these have further subtrees. Is that
That's
correct?
Yeah.
Yeah.
So what we've
I
got
think
to do.
that number is actually for the other Pythagorean theorem that I found. I just not re-related it.
Okay.
I know because there is just some pi thag and pi thi. I don't know what's the difference immediately.
Arbitrary inner product. That's kind of weird. Can we just search for what was the one that we used in the other blog post?
I found this one.
Is this the same one? Oh, Pythag.
Yeah.
Okay, so let's use the Pythag one. And oh, we're finished here. Okay, so Pythag. How do you know in the trees? Let's see, we want to say tree graph.
Aspect ratio.
Oh, for God's sake, tree graph percent 795. The hell's wrong with that? What's going on here?
This is like this way out back again. There's still a back with way out of tree graph.
Has it been reported?
Yeah. I've seen it reported already.
Okay.
But that's a tree, a graph, isn't it? Why isn't it giving me the edge list?
Now we're trying to take another cell, not percent, but percent 796.
Okay. So this is the Pythagorean theorem. So what level did that prove it to? So if I want to go to level, what does it look like on level 1? How do I get that from the tree? Do you know how to do that?
What do you mean? Prove it to some level.
I just want to get the part. I just want to get the top level of a tree. Get what I'm saying?
Yeah.
Maybe tree level.
Tree level. List of subtrees specified by a given number of indices. No, I want just the top of the tree. Okay, that's very confusing. So how do I get just the number of elements on That's crazy. It's crazy, crazy, crazy. Okay, so I can just do vertex count on 800. Okay, so that's the number of vertices, but each one of those vertices could itself be a subtree, right?
Many of them,
Many of them.
because
Right,
some of them are just axioms.
Okay, how do I get the top of this frigging tree? How do I get the top of the tree that's just the first level?
What about trees? What? No, not at this.
Why not tree extract? Like,
Yes. Hmm.
Makes sense.
what is bug?
Some. But I want to get only down to a certain level.
You can use span for tree extract. So like 1 semicolon, semicolon.
Okay, well, actually, what I want to say is tree level. And then I want to say the level spec, which is 0 through 1, for example. I meant 795. Oh, come on. What the heck is it doing here? What is this doing? What is this garbage?
Subtrees. It's like children, right? All the children at this level.
Yeah, well, I just want the top of the tree.
You can. I had this function somewhere manually defined because I feel like I think I can find it. All right from scratch.
What is it? The root node?
That function called tweetake.
Is it yours or is it?
No, I haven't pushed it yet. I can just paste it into the chat. It's a short one.
Yeah, okay. Okay, that's more like it. Now, why does it start off with 3 equi-TRD?
That's
Why
some
doesn't
equality because it's always equality on the top, and this is
Okay.
some equality. Yeah.
So is this going to wind up being? What happens if I just say tree of that aspect ratio, arrow half? Okay. So is this basically an expression here? Note is this 3 adant 3. Well, let's go to the Pythag.
No, not that one. That's Pythy.
I can use the same. Okay. So this up here better be, I don't understand. So the whole thing is Pythag. And then what's W3A, CO, 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 et cetera, et cetera. CO must be a constant.
Hmm? Yes, Nick?
Well, it should be the first one. I'm not sure where it's missing. I see a free addend there,
Yeah, I see that too. It's number 7.
but maybe it's not just reference the name of the first action. The root node is not referenced anyway. In this explorer, I guess.
Is there a tree count, tree size? The number of subtrees of a tree. So if I say tree size of the original of tree. Okay, that's that. Great. So what I want to do is I want to go tree size. I've got to recursively go down tree sizing things.
Okay.
Have I not? I mean, I've got to do a tree map, but it's really kind of funky because I've got to do a tree map. I've got to go all the way down, right, until I hit Axiom. So let's just check that if I go here and I pick up an axiom. Okay, let's just check. Oh, I see. I just do that. So I say metamath proof of AX3.
Yep.
What alternative do I have to tree? Do I have something different from tree?
There's some graph, expanded tree, expanded graph. Oh, and it only works for theorems, I guess. If you want an axiom, you just take MM without and extract it from there. That's all the information.
Okay, which part of MM?
Statements. So MM is just a association. So statements, and I guess you have to find it there.
It's a lot of statements.
So, MM. Do it.
Oh, there we go. There it is. Axiom X3. Okay.
Yeah.
So
the
this is
second
just
element.
yeah.
The second element is just a list of constants and variables that corresponds to the statement.
Yeah, you can see
Of
it.
this axiom.
You can see it on the metamath page. WPH,
this is, yeah.
WN.
Yeah, and this is then the proof. But so
No,
what
proof
we
is
want,
empty. That's the input. It's
okay.
like this axiom takes two hypotheses as an input.
But okay, so what we want to do here is to take these statements and we want to run down what is pH here. Like if I say statements pH, no, it's not there.
It's a symbol. It's MM symbols.
Oh, is it phi and psi?
I
Yeah.
see.
Yeah.
That's fine.
Yeah, it's phi and psi. Yeah.
Okay, but so what I'm trying to do is I'm trying to get the Pythagorean theorem, not the proof of the Pythagorean theorem.
Yeah.
Okay, so look, analogy, okay?
Mhm.
Statement of Pythagorean theorem, proof of Pythag, which is the past light cone.
Entailment cone,
Yes,
not emulation cone.
past entailment cone. Am I correct? Where it will eventually back to the axiomatic Big Bang.
Well, that's our framework.
Yeah, I think it's right. Okay, so this is the proof of Pythag. So we've got the thing, this is a tipped upside down thing where our entailment cone is, and there should be, okay, where's is Pythag a root of this?
Yeah, I think if you actually ask for graph, create this additional vertex.
Oh, I see. So if I say this, and I say graph, well,
Yeah.
do I?
Mm.
Yeah, that tiny vertex on top, I think it's going to be Pythag.
Okay, why is there so little in this? I mean, well, there's much less in here than there is in there. How
Well,
come?
because graph is also deduplicating, right? So
This is, or this is.
The graph.
graph deduplicates all the nodes.
The tree is
Oh.
not deduplicated. Can we check to see that Pythag is on top there?
Yep.
Ding ding.
Okay, so this is the right thing. This is the entailment cone. Okay, so this is in fact the entailment cone.
I mean, it's the deduplicated entailment cone.
What's wrong with that?
Nothing. It's just a.
Okay, what are these? Why is this law cause there? Why isn't that? Oh, I see. This is, okay, so this is entailment cone. What are these? What's that? Cos alpha pi, cos alpha pi, cos half pi, cos half pi. I see, that's a constant. So
Red
C,
nodes are inputs.
okay, but this has not, this doesn't go all the way back to axioms.
No, it's not expanded graph, but you can also expand it. But I
How?
guess it's going to be
How?
the
How do
same
I?
as it
You can say
was going to
expanded
be
graph.
giant. I already
Right.
tried it. It just expands the tree and then also deduplicates the expanded tree.
Is there a way to limit the expanded graph to only go a certain number of levels?
No, not yet.
Can you sample it, Nick?
No, I don't have like built-in.
Can we
You
just
can try
modify?
it for a smaller. You can try it for a smaller theorem or something, just to see.
What would be an
Okay.
example of a smaller theorem?
I wonder if I don't know.
Am I
Nick-
correct in believing that what's going to expand is only the red nodes? Is that true?
No, red node's exactly what's not going to expand. That's just verbatim inputs to the theorem. It
So
means,
those are going to stay like that? They're just going to stay kind of dangling out there?
yeah.
But
what-
what should happen is there's just going to be axioms at the bottom that eventually lead to the theorem we want.
Axioms and this kind of inputs.
What was an input?
The red ones.
I know, but what do they mean?
No, because there's like a freedom to the theorem. It proves something about all the things, and you have to provide the things first. It's like for the Pythagorean theorem, I guess its inputs are all the sides of your triangle, right? And I don't know, variables. And that it's actual right triangle or something. You have to provide it.
Okay,
Prove that your triangle is right.
Right. So
okay, but so for us, those are just symbolic variables. So we leave those as dangling ends. Is that right?
Yeah.
I'm a little confused by that. Okay, so
Those are
now
just
when
variables.
okay, but now what about the statement of the Pythagorean theorem? Not the entailment cone, but just the statement of the theorem. So I believe that that would be MM of statements. Whoops.
statements. Yeah.
Oh no.
Right.
Okay.
How
How do I read this lovely thing?
Is this where the stat comes in, Nick?
Oh, you don't have to read the proof, but the statement is that second element again, just a sequence of constant
Okay,
variables.
but then what do I have to, but I have to interpret that statement, right?
Well, yeah, your proof is like a program that produces the statement in the end.
I understand,
that-
but yeah,
Yeah, that constitutes the proof. That's all.
I know. But if I just want the statement of the theorem without having its proof, how many eames?
This is your statement.
Okay, but it must depend on things. Like these weird things must be, they must be defined in terms of lower level things.
What are
Well, in
those?
MetaMath, they are just defined as constants and variables. You just state them at the beginning of your library. You have just a list of variables and constants. There's nothing beneath that.
But the notion of a square here.
Well, it's not a notion, it's just a symbol. But you can just use those symbols really needed to just provide any proof of any theorem. You have to actually construct it with a program using just some programs that you defined as axioms, right? But the statement is just a sequence of constants and variables, nothing else. They don't depend on anything. You can encounter them in some other theorems. So you can only define them relatively to other theorems, and that's it.
I am irreducibly confused.
Well, one question that I have, Nick, is, in our framework, we have this machine level, this level,
Yeah.
and we can ask questions about where does addition come from? And you can start to think about that in terms of combinators. And what I've kind of suspected is that MetaMath is not that foundational. It doesn't go down that
No, it
deep.
can go any lower.
No.
It has names.
Yeah, exactly.
But you can canonicalize those names, just get rid of them.
Right.
So just look at canonical names of symbols and all the constants there. And then you just look at the theorems with canonical names, and that's it. It's
yeah.
But so let's look at the Pythagorean theorem here, if we have it. No, how could it not be there? How could it not be? Oh, wait a second.
Maybe it's classified under something.
Oh gosh, this isn't the most recent version. Okay, hold on.
Yeah, there it is on the left.
Oh, that's the whole thing. What is it taking so long to do?
Mm-hmm.
Okay, so for us, we would define these operators, if I'm making sense.
You say we, you mean in our framework and not in MetaMath language.
Right.
Okay.
Right, we've got this. And the question is, how does that compile down to Eames?
Well, that's the question. My God, how does a triangle compile down to? What even a triangle or an angle?
It's just a symbol. And the whole point is, what does this compile down to? This compiles down to,
It doesn't make sense without axioms.
I know.
You collect axioms. So that's the question, how they compile to combinations.
Yeah.
Yeah, right. But I mean, this.
I don't think we have them here, unfortunately.
Okay, well, I have them in chaos. Oh, what the hell? Let's just pull them in. Right one.
Wow. NKS.
Let's see. No tautologies. Yeah, but where is? Oh, that's that one that we were looking for what it's worth. I mean, clearly we don't need all the.
Oh yeah. For draft 04.
Oh, look at that. How convenient. There's a separate whole file for that. And there you go. There is geometry. Okay, so here we've got things like this B for betweenness.
Oh, great. Okay.
So this is
Okay,
the I mean, I wonder whether we should pick a theorem in arithmetic. What's the theorem in arithmetic that isn't crazy? I mean, the infinity of primes, I guess, is one possibility, but that's fairly advanced. I mean, we could have where should we do this? I mean, so some of these. Gosh, these are pretty advanced.
Yeah.
But so the goal here is to find out Yeah, the goal is, again, what we're trying to do is these two questions. One is, how big is the theorem statement in
Yes.
terms of, what we want is okay, so these are axioms of geometry. And now what we want is need a theorem statement in the language of the axioms,
Right.
and
And
B,
the entailment.
theorem proof,
Yeah. Entailment.
right, in the language of the axioms. Okay, so one might have thought that the statement of the theorem was just a point, but it's not. And I'm a little confused by this because in our setup of these accumulative graphs, the theorem statement is just a single point.
Yeah.
So how do we assess this thing about how big is the, and the problem is that what we're saying is what gives a theorem a non-zero size.
Mhm.
We say what gives the theorem size is the quotes uncertainty in its underlying axioms. Which is not capturable in MetaMath, if I'm not mistaken. Is there any proxy for that?
Well, if you take multiple libraries of MetaMath with the same theorem, maybe.
Yeah. But that doesn't seem right because well, but hold on. Each of those, in the stuff that we've done, a single theorem is a single node in the entailment graph.
Yeah. Yeah.
So in what sense? So what we're saying is that each theorem is a node, but we don't know which theorem we've got. I mean, you know what I'm saying? I mean, okay, there are lots of micro theorems, so to speak.
So what's a micro theorem?
It's a theorem that we consider equivalent to the Pythagorean theorem. So for example, in this case, what we would be saying, Egypt in MetaMath, Pythag and Pyth-I are both statements of the Pythagorean theorem. But let's see whether we can, whether we've got it. Even though they are different sort of atoms, they're different. See, in what sense are those things eames? Oh, I'm so confused.
They're
axiomatic expressions that are built out of, that are then broken down. See, I think what we're doing,
they constructed from eames because the future entailment cone of the axioms. You can construct them.
I understand, but they're statements. What we're looking for as coarse-grained observers is how broad is our, how broad is the thing that we call the Pythagorean theorem?
Okay. And when you
Right,
say,
'cause that's what we want to know.
When you say broad,
I mean that there are many different emic statements
yes.
of the same theorem.
Yeah. Okay. So it's a cloud.
Yes, but the thing is, it's a
Yeah.
cloud
Yes. Okay. That's what I thought.
where it follows. See, what's confusing to me is there's in these two different MetaMath libraries, we've got two different mathematical big bangs, and that's yet a different sense.
Yeah.
We want, same MetaMath library, but different. Well, is it a different proof? It's not good enough to be a different proof, but different.
It's a different proof, but proof graphs are similar, maybe even isomorphic.
Yeah. Is it like the section on quantorial?
No, it's not, because the whole point is that these are nearby. Okay, look, same MetaMath library, but different outcome statements. Okay, so this is in the entailment cone. In the full entailment cone, the Pythagorean theorem is a region in branch Hill space. Do you get what I'm saying?
Are you actually certain that it actually makes sense? Why there should be necessary more than one Pythagorean theorem, given just one set of axioms? Why it's not unique? Maybe it's not unique for us, for humans, just because of like an artifact for us naming stuff differently and actually
sure. It's just like
between universes.
Okay, same point with space, right? There is a notion. If I point to a particular place, I could hit a single atom of space, but I won't. I won't know which atom of space I'm talking about.
Fine. Yeah.
Right? And similar here, I don't exactly know which Pythagorean theorem, because there can be differently stated Pythagorean theorems. That the proof graph leads me to a different place. In other words, I interpret them as the same Pythagorean theorem, but it isn't in fact the same destination in mathematical space.
Yeah, I see the idea. Just is there an actually concrete example? Maybe not for Pythagorean theorem, but some theorem.
Okay, so let's think about that. Let's think about it. Let's think about it in terms of successor functions for integers or something.
It's like you can make an integer multiple ways, multiple.
Right. So, example of theorem cloud. There are multiple ways. Well, okay, so at the axiom level, the axiom level, 2 at the EAM level.
At the EAM level, right.
Right, at the EAM level, e.g., there are many ways to make an integer. Now, at the axiom level, let's see, there are many. What's a good example? I mean, I've been using the example of the Pythagorean theorem could be based on different axioms. Okay, so there's case one here, which is same axioms, different statement. And case two is different axioms, I think.
Isn't case one is just the same as im level difference?
As which?
As your
Same axioms, different
second
statement.
bullet point. Like different statement is just saying like there are different ims.
I'm not sure that's right. I think that it could be a different statement. Well, maybe you're right. Maybe you're right. So then case two, different axioms. Oh gosh, how do we think about that? Because that looks like it's a different entailment cone.
Yeah. I guess just like some graph isomorphicity between them. The only way.
Actually,
You can
that's not right,
unify.
because we could, no, look, the whole point is, throw in many axioms to the original Big Bang.
Mhm.
Now, any particular version of a theorem might pick out different ones. To use as its foundation.
Okay, yeah. So your
In other
past
words,
entailment cone
what's
can
that?
contain multiple. Your past entailment cone will contain multiple Big Bangs.
Yeah, but I mean, but that it isn't really multiple Big Bangs. It's just the Big Bang is bigger than you thought, and it has more
Yeah.
Yeah,
distinct.
yeah, that's fine.
Okay. How on earth are we going to estimate the size? Okay, so the entailment cone, we can sort of estimate it. Okay, the first question is we got a statement and it can be compiled down into eames in some way.
Yeah.
But that doesn't tell us how big the region is.
No. No, it doesn't.
What is the analog of compiling the statement down to eames in physics? Yeah, the answer to that is, actually, that's how we get an estimate of the size of the theorem, is we say, how does it compile down to eames?
Yeah. But how do
Because,
we do it?
well, we have to take, okay, there's two different things, okay? Okay, so size of a theorem in eames is take the theorem statement and write it in the language of the axioms. And then even lower level.
Yeah.
Okay, so
Why don't we try doing that for a very simple theorem? Something that's tractable.
yeah, I understand, but how do we do that from MetaMath? Is there a way to do that from MetaMath?
Well, you can write each statement as a proof using just axioms. It's like expand tree that they have there.
Okay, but wait a second. So
But we can't do it for Pythagorean theorem because it's too big.
yes, but I mean, my question is, that's writing in terms of its proof. What about just the statement of the theorem? independent of its proof? Or is the proof basically giving the statement of the theorem because you have to define all the operators and things like that?
So Nick, when you take let's say you have a simple theorem and you take the expanded tree, what do you find at the end?
Well, the end is just the last substitution that makes
Okay.
your
Okay.
statement.
Okay, I think it's probably Nick. You probably have to go soon.
Yeah. No, I can stay for a while.
Why? Because it's 7
A little
o'clock in
bit
the
longer.
morning.
Well,
Right.
yeah, I mean that's what I was concerned about.
Yeah.
Okay. All right. So look, I'm pretty confused here, which is probably why I was having a hard time writing this section.
There's some outstanding theoretical work to be
Well,
done
hold
here,
on.
Steve.
So what we're saying is, and by the way, we've also got this section which we have not yet really filled in, which is called empirical metamathematics, which we started on. We got those paths to those things, right?
Right.
And this is basically showing us, given our normal axioms, how far do we go in the entailment cone before we get to these things?
Right.
Now, each of these things looks like it's a point. Oh, what is we doing here? So we're saying, as an observer, okay, what does an observer do? Okay, what does an observer coarse grain? And the answer is one thing they do is, one, the observer doesn't care about the proof in a first approximation. So they coarse grain all proofs together. Actually, the zeroth thing, the observer doesn't care about the names of variables.
Okay. Yeah, that's fine.
Oh, it's also related to the fact I realized today during Jonathan's lecture about homotopies and proofs.
Yeah.
Like an observer is a homotopy between proofs. When you do when you're doing a completion, right? And
Yes.
that actual the proof graphs is like building up the group weight, right? Because each depth, each level on the proof graph is like an additional homotopy level. So you're building this homotopy tower. Actually, haven't realized it before.
Say that again.
It's like much. That's the proof graph is like building homotopy tower. So each substitution lemma in equational logic is like building up a completion, right? And if you use those rules again for another lemma, you're like doing another
higher level one
step in this tower.
Yeah, a higher level one, because they're all equivalences. So you're kind of weaving together this quilt of higher and higher equivalences, right?
Why are they higher and higher?
Well, because it's like you can treat one equivalence as some path, right? And then if you're going to take equivalence between that and something else, you see, you have to go up.
Okay. Was Jonathan talking about mathematics stuff?
No, I just asked him the question about this particular thing.
And these clouds also have that similar property.
Which, yes, I mean, but okay, the point is different proofs will not be shredded in the same way that different axioms, different axiom situations might be. In other words, the fact that a blob of atoms of space.
Yeah.
Okay, so the analogy is, quotes, nearby atoms of space might have had different histories. Yeah, but the point is that two nearby atoms of space might have come from the Big Bang. Their path from the Big Bang might have been different.
Fine.
Which is the same as saying CF two proof paths.
Right.
Okay, but nevertheless, because they are nearby in physical space,
yes,
we conflate them for practical purposes.
Well, that's why I was asking about the quantorial section and those diagrams that we have. Not that this is the same as content-wise as that section, but we were looking at, you have all these different paths and you want to see how connected they are. That's why I was asking about that.
Well, wait a second. So, well, I think what you're saying is,
yeah, those.
Okay. So what you might be saying,
yeah,
is that two different things here might be called the same theorem, basically.
okay.
That's what we're really claiming, is that two different things, two stated differently things might be given the same name as a theorem. That's the claim we're making.
Okay.
And the
Even though
shredding
there's no
claim,
even though there's no edge between them, so we can't prove that they're equivalent.
Right, exactly. That's the whole point. Yes, that's the whole point.
But
okay,
why can't you wait? Hold on. Why can't you prove that they're equivalent?
Oh, because they're probably not. They're not equivalent except to the observer.
Okay, so you're not proving that they're equivalent, but you are equating them, or not equating them, but you're coarse graining them so that they are equivalent.
Yes, and coarse graining them, saying both of these are the Pythagorean theorem, even though one has a different nerdy treatment of the way that you take a square or something.
Well, then the question is that worth representing? So we have paths that are proof paths, but then how do we represent the observer's conflation of theories in a cloud?
Well, they're just nearby theories in mathematical space that get conflated.
So you don't want to draw conflation edges in a different color, or you don't want to do something to kind of visually represent that these can be brought together in some way by the observer.
I don't think so. I mean, I think Well, okay, it will be good to have a toy model for this. 1 second, I'll be right back. Second.
I don't understand, like, how can you say that theorems are near each other?
I don't. That's a good question as well.
I think
mean-
it's like, as soon as you find the nearby in quotes theorems, you can, I don't know, add a completion between them.
Well, that's what yeah, right. That's what I was asking. I mean, that's the thing, which is it could be that what's right next to the theorem is actually something that you could also prove using that particular path, and that the equivalent Pythagorean theorem is actually very far away. And that what's nearby is not the same theorem, but it's something that is related in the entailment cone, but is semantically distinct. But syntactically kind of nearby. And if they're far away, that's why I'm suggesting we have some way of, I mean, this is observer theory at this point, which is you have something like this, a multi-bang entailment cone, and you want to show how observers coarse grain. Multi-bang is probably not a good term. It sounds that's not quite right.
Oh yeah.
Nick, what's a theorem? Like a theorem for which the expanded tree isn't too big. What about 2 + 2 = 4 or 1 + 1 = 2? Is it still really big?
Maybe not.
Okay.
You can try it. So
Okay, we can try that. Okay, we
2
can try
+
that.
2 = 4.
Okay, so yeah, we have some further thoughts.
Okay,
Nick,
go ahead.
Nick, you want to share that question you had?
No, yeah, well, about the nearness, it's like I don't understand. Like, if two theorems are near each other, is it like always possible to like add more rules, like completion rules, to actually equate them? So they right?
Is it always possible, you're asking?
By measurement, yeah, because completion is like measurement. So if observer doing measurement, so it seems like nearby theorems should be equal up to some measurement.
That's yeah. That's
after measuring them.
That's what I
For
was getting
observer,
at.
they're still gonna be equal. They may be different, like truly different in our like IMS or the multivariate graph, but observer is still gonna see them the same.
Yeah.
The same.
If the observer, well, okay, how does that work in the spatial case? Then what we've got is essentially, I think, a causal graph. As opposed to a multi-way graph.
That's interesting. Now, Nick had another question. Which,
What question?
okay, fine. Nick, I'll recall on your behalf.
Well,
The other question that Nick had was, why do you presume that theorems in a cloud are nearby? And I guess the point is, so let's say you have some entailment cone, some entailment cone that has multiple big bangs, so to speak, in it, or something like that. Okay, and it gives rise to the same theorem, but they're somewhat distinct. Okay, so they're semantically distinct, but what if they're in completely different syntactic regions, and what's nearer to those theorems are not its kindred theorems, but are just other statements that are nearby, syntactically when you're doing entailments in the cone. Why are they nearby? Why are they proximal to each other?
Well, I mean, that's the point. The point is that nearness to the observer, semantic nearness to the observer, better be essentially the same as syntactic nearness, or the observer is conflating together, destructive interference from the opposite ends of the universe.
Well, not necessarily syntactically the same, because as mentioned before, the measurement by completion is a rule between terms that shouldn't be syntactically the same, right?
I mean, they're gonna if you have, I mean, even, I don't know, Pythag and Pythe, if you look at them, in media res, they're not the same, are they? I mean, they're going to differ. That's the whole point. So you do have this destructive interference business does arise, but when you're coarse graining and you're looking at a nice friendly cloud, it's fine.
Hold on, let's walk through that. So you're claiming actually, what are you claiming? You're claiming, because maybe we can find the analog of destructive interference here.
Yeah.
Okay, so explain that.
Well, the
claim will be that, if you're going to conflate Pythag and Pythe, by the time you've done that, you've conflated two things that are basically at the opposite ends of rule space.
Well, what I'm suggesting is that the conflation, if you're saying that they're part of a cloud, so to speak, I mean, this is a semantic observation you're making. But syntactically, then in this cone that has multiple big bangs in it, some multi-germ cone or what have you, it's those syntactic paths could differ. They could differ, and if they differ considerably, they're going to be somewhat distant from one another, these two conflated theorems in the cone, just because of how the computation works spatially in the graph.
Well, I think what we're saying here is Pythag and Pythe, if those are conflated, what the heck does that mean? Yeah, I know what it means. I mean, somehow by path counting in the entailment cone, you never get to that confined thing. Well, that doesn't make sense. Yeah. Okay.
What it mean? Oh no, go ahead. If you were.
Look. If you conflate Pythag and Pythe, then you are also conflating a zillion other intermediate results.
Yes.
And that's like entailing false.
Wait.
Because you've got all this crud that you've entailed.
How do I explain?
But this is the thing, Stephen, which is the question is, so on the one hand, yes, you have to be careful you have to be careful that absurdity doesn't, undo your entailment fabric. So we have this notion of false, right? Okay, so there's that. But there's also this claim that you have that observers can afford to coarse grain, in some instances.
I know,
but hold on.
Yeah.
So for here, you have these two different paths. And if you look at them in media res, they differ and there's destructive interference. But when you take the whole path, once it's done, it's arrived at the theorem, and you have, say, some forgetful functor from one path to another where you're mapping back and forth and you're not thinking about its contents necessarily, you just know that those two paths are basically equivalent, the point here is that that's a coarse graining, that's an equivalence that the observer can afford to do. It's not the same as, say, a Rulio virus case, because you get the same theorem in the end. So you can view them as equivalent.
You're right. But what does it mean that you entailed all this intermediate stuff? So I'm saying, I mean,
Yeah.
it goes to a
They
lot
all
of
entangled, right? Your PyFag and PyPhi is just two nodes in the branch of graph. And yeah, and there is a bunch of CRUD in between.
right.
So if you measure the slice, right, you conflate them, and you conflate all other nodes in the branch of graph between them two.
Okay, what does that mean? I understand that, but what is the analog of the destructive interference? That's saying that we can. What's the analog of the quantum phase?
Well,
Nick, you want to take a shot at that?
I don't know, because I don't think we still understand that, how the phase works.
I mean, one less significant thing that can be said is, on the one hand, when you have a cloud like this, I mean, what it means is Pythagorean theorem has a certain proof density. This is some concept we talked about before. I don't know if we've introduced it in this discussion. So it has some proof density. And on the one hand, with proof density, it means, well, maybe this is something that's important because you can arrive at it in different ways. And so in some sense, it's computationally favorable. There are different kind of ways of constructing it. And so there are different ways in which computational processes, tend towards it. So that's interesting. But on the other hand, it also means that you're doing more coarse graining. And when you look at these paths midway through, there's the destructive interference there.
Well, hold on.
You get both of those.
The first point is there's path counting of the number of ways to get to this theorem.
Yeah.
Right,
right. So it has an in degree.
Well, more than that. I mean,
yeah, fine.
Because the thought path has I don't know what the significance of the path counting is. That's in in the entailment cone. How frequently is the theorem reached?
Well, it's the proof density.
No, I know that, but what is it? What is the significance of that?
Some analog of energy, mass.
Yeah, I know, but what's the significance for mathematicians?
Probability, wave energy.
Yeah, it's probability. But what is, people don't talk about the probability of getting to a theorem in an entailment cone.
Well, people don't talk about entailment cone. Yes. But anyway, we don't talk about the probability of that. We haven't. That's true.
Right, but then the statement that, okay, one statement would be proofs are very distant in the intermediate stages of getting to a particular theorem. Another is there are two different versions of what we call the same theorem.
Yeah.
Now, I guess you might claim that two paths that land up on the same theorem, that at an intermediate stage, you might, this is where it's tricky because, look, the fact is, okay, with expression rewriting styles of graph, we can have things like we have things like this. Here we go. This one here. Where in fact, everything is equivalent to A here. But there's a theorem this theorem here, A is equivalent to both this and this. That's, okay, hold on. What is our cloud here? We have to decide what we mean by it being the same theorem.
We'll start from this one and then add completions, all the possible completions, like build this tower, homotopy tower again, of rules until it saturates. Maybe it's even saturate the whole multivariate graph. And
yeah, I understand, but although that's easier with the accumulative case than this case, isn't it? No, I see what you're saying. You add that rule.
Yeah, I think accumulative case is like, it's a straightforward way of actually building the limit, I think. So like when you do it accumulatively, you already, the limit of this accumulative multivariate graph is the same limit as just having a multivariate graph and build this infinite completion tower.
Yeah, that's
interesting.
It's
the same limit.
Yeah, that's interesting.
Okay, it is interesting. I agree.
Yeah.
Okay, well, so hold on. Here, what is the analog? What on earth is our cloud here?
Well, I'm kind of confused because on the one hand, I understand the cloud concept with something like Pythag and Pythe because they're different, right? But we're saying the observer conflates them. Here, this bab. I mean, it's just singular, and there are just different paths that arrive at it.
But in intermediate stages.
Yes. No, I understand that the paths are distinct. And so
no,
you
but
could,
we could say that the theorem that AAA equals A is somehow related to the theorem B triple A B equals A.
Right.
That's the sense in which those could be, two theorems in a cloud.
Right. So is the cloud just what you get after you run all the completions?
Well, no. After you've done the completions, the cloud is compressed to a point.
Yeah.
I
mean, then it's an unambiguous object.
Yeah, I know. But what we're saying is there's still, at this level, AAA and BAAB equals A. Both of those are theorems.
Yes.
We're saying those are theorems that might be in the same cloud. Okay.
Yeah.
Now, the question would be, if the theorems, to say that the theorems are in the same cloud, even when they're very far apart, or even perhaps in disconnected subgraphs.
Yeah.
Is what will go wrong if you do that? It means if they're far apart, there's nothing in between them. What does that mean? What does that mean for?
Well, so hold on, Steve. If I understand what you're saying, if you're just if you're positing that they're both in the same cloud, okay, but they're both just these paths that haven't actually become confluent yet, right?
Yes.
So you're then you're in danger of being shredded, right? Because I mean, in this case, it ends up, I suppose, being all right with a given rule. You get there, but couldn't it be the case that you could get that exact same two paths? Well, okay, maybe there are certain cases in which you could get those two paths with a different rule, and in that case, they're not confluent, and then you do end up getting shredded.
Yeah, right. They go to different places.
Right, exactly.
Right. That's the point. And I mean, but the thing is, I see. So maybe destructive interference. Yeah, maybe destructive interference is you can't believe both things at a time, which is what we've kept on believing. That's destructive interference becomes can't believe, you can't believe both branches at the same time,
right?
Because you'd get shredded.
Right. And so in some
They go to
sense,
different places.
Falsity is like there's no cloud that supports this.
What do you mean? No cloud that supports what?
Making the equivalence.
And falsity.
Yeah.
There's no, that however close you are, it'll still just blow up.
You just don't have the grounds to, like, let's say you posit that there's that equivalence. Let's say you would only run this for 2 steps or something, right? And you start to ask if there's some equivalence between those two, right? Well, there's still more irreducible work that needs to be done before you can establish that they're confluent, and then you know that you have a cloud. But because you don't, well, hold on.
Yeah, look, confluence
is a little complicated
related to this, but the whole point is that destructive interference means you can't believe in both branches at the same time.
Yes.
And let's see how that relates to physics, destructive interference in physics. Okay.
I think to be honest, it'll be important for a lot of multi-computation, economics, maybe immunology. This is an important general principle.
Yeah, probably is.
Yeah.
Right, but okay, so then you can't, the observer who tries to conflate things that end up in different places, that end up with different that are far apart.
Yeah.
What is the analogy in physics? That ends up being far apart, but the observer is trying to conflate them. And then the statement in physics is there is no photon there somehow in the end. Because you tried to conflate the thing where okay, the photon wound up being at a different place in branch Hill space, going through the 2 slits. And I see. If going through each slit was in a similar place in branch Hill space, you could perfectly well just say, I'm conflating these things.
Okay, fine.
But I think the basic point is if they wind up in such different places, the observer will never see them, because the observer, the point is, okay, the point is the observer has a certain range of okay, so let's take the physics case.
Right.
Okay, so the physics case is observer has a certain branchial range.
Right.
You know, how far do they see? How far are they sensing?
Yeah.
In branchial space.
Right. And you can't ask them to scope over some broad range and still be an observer. You can't do it.
Right. And so the basic point is that in the, between the slits, so to speak, what's happening is it's too distant in branchial space. The passage of the photon through each slit is too far away in branchial space. So what's happening is the observer, therefore, I don't quite understand in the case of this picture that we have at the top there. I mean,
can I throw some idea that I'm just thinking about?
Please, Nick.
So it's about those completions again. It's like, how can they relate to a face in the end? Because I'm not sure. It's like when we are trying to conflate two vertices in the multivariate graph, right? They connect in the branchial graph by some number of edges, right? And then you start to add more completion rules. You do it one time, you go one step higher in this homotopy tower. You do another completion step, and you do one level higher again, right?
Yes.
What if you do like path counting after each of those steps and like compare them?
Okay. Yeah.
So it's like, would it be like the relation of path counts on all of those homotopy levels somehow relate to this phase in the end, and how they destructively interfere or constructively? It's like, for example, if you add one more completion step, you just add like the same number of paths that you already had, right? But if you add one more, it's going to be some kind of.
Okay, so what you're saying is, let's label the number of ways to get to a particular. I mean, we have that actually. We have this this concept of a weighted branchial graph. Let's see. Weighted multi-way graphs. There we go. So that's what you're talking about. Is that correct? Oh, and that's without completions.
Yeah, it's like the first level. This is like without completions, this is the separation between them. Then you add all rules after completing all the multi-way steps that we already have. And you draw a branchial graph again, weighted branchial graph, right? And you kind of do it with like infinite number of completions. Or maybe it's actually going to be finite.
No, finite number of completions, because an infinite number of completions, everything will just turn into a single blob.
Yeah.
And well, the other thing is, Nick, what about if completions aren't always possible and you have some obstruction and you actually can't reduce it to a point? I mean, there are probably cases like that too.
Well, if there isn't causal invariance, then you can absolutely not be able to do it.
Right. Yeah.
Yeah, I don't think it always just shrinks to a point. It depends how you actually do completion. It's not necessarily Knut appendix completion when you have some kind of order of your states. Maybe you just do some co-substitution and derive it, the new rule again.
Is this just a commercial for co-substitution?
It's a critical dilemma, yeah.
Very good
It requires
salesman for
substitution.
co-substitution.
Well, it is. Yes, it is a critical dilemma. Right. Okay, so you add random critical pair lemmas, basically.
Yeah, you just
And
add
that compresses
rules.
this. Yeah, that compresses this graph. Okay, but I'm still
Why it
going back.
compresses it? You have more edges, so you have more parts.
Yes, I know. It compresses as in the sense that the diameter gets smaller.
Yeah.
Okay. So my question, coming back again to the interpretation of this. Okay.
Sure.
In physics, the interpretation is an observer who is averaging over a certain branchial area will conclude that there's nothing there in the destructive interference place.
Yeah.
Kind of the idea.
Yeah.
Okay, so what's the analog in mathematics? The analog of the observer saying, oh, there's nothing here because my range and branchial space, I can't see anything within my range and branchial space. That would be saying what the heck is that saying? That's saying there's no theorem. So I'm looking.
Yes. Yeah.
I mean, there's no theorem that I consider to be
Yes.
this theorem, so to speak, that I consider to be compatible with this theorem. There's no such theorem, even though well, is it perhaps a statement that of the non-convergence of these paths?
Yeah.
Yeah, but how does that work? So I mean, the non-convergence of these paths, you wind up with in different proof paths.
Yeah. Yeah.
What the heck? I mean,
Wait, no,
when do we
hold on, Steven, just to refresh. Are you considering you're looking at this graph, for instance, but somewhere in the middle and it hasn't completed yet? Okay.
Yeah, that's what I'm saying.
So destructive interference, you're saying, I don't see these proofs yielding some common theorem. I mean, isn't that it? They're not yielding some result that I find to be the same so that I can make them all equivalent. They're going off in different directions. And it's not advisable that I consider these different directions to be the same, because if you just do that in the general case, you're going to get completely shredded.
Yeah, okay, but let's walk through that. What does that really mean? That we've got two theorems, you've gone off in different proof directions.
Yeah, so hold on. So what this means is you have these two different evaluations, and it's basically syntactic at the moment. And you're saying whether or not semantically you want to view them as distinct, right? And the threat is if you start to assign semantic equivalence between wildly different evaluation fronts that are syntactic, when you end up assigning semantic meaning to them, you're just going to be accepting as equivalent all kinds of syntactic nonsense, and that's going to be shredding as an observer, right?
Okay, the thing we have to remember, here's an important point we have to remember. We think about things in terms of the mathematical Big Bang, coming from axioms that we believe to be true in some sense. Yeah, this is an important point. This is an important point. This is the important point. That the initial condition contains not just the axioms we want, but all other axioms as well.
That's right.
So if we try to conflate things that are too far apart, we might be gulping in random other axioms.
That's right.
Which means we're concluding things, which means we're concluding things that we consider garbage.
Yeah. Yeah. So put differently, our entailment cones, they emerge from the level, from the Eam level, which includes all possible syntax. And you don't want to assign semantic truth to just all possible syntax, because then you end up with absurdity. And that's why we have this notion of destructive interference here. Because it's only under certain conditions that you want to actually assign semantic equivalence between your different proofs.
So the basic point is, if the proofs get too far apart, they will go into zones that have contribution from axioms you didn't want to be considering.
That's fine, but there's another question I have here, which is this question of too far apart. So let's take a counterfactual, so to speak. Okay, let's take this graph, and you see you have A goes to AA, and then take any two of those, like AA goes to AAA, or AA goes to BABA, right?
Mm-hmm.
So, okay, but let's say that's all you have. Okay, you've only run this for 2 iterations. Those are near each other. According to what you've written, right? You're saying if the proofs get too far apart, blah 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 blah. There are these risks. But even at 2 iterations, these 2 things, AAA and BABA, I mean, those could prove to be wildly different. So I guess the challenge here is, you're saying if they're too far apart, but what about in this case where they're actually right next to each other, but without further knowledge, they could end up being wildly different, couldn't they?
Well, I was thinking of a different thing. That is that what we're doing is we're pulling stuff out of this ocean of possible initial conditions.
Yes.
And in some appropriate local region, we're okay saying we just came from a given, initial axiom. That's probably okay to do.
Why? But that's the question. Why is that okay? Like, is that the example I just gave is a kind of a local region?
Yeah, I know. I understand.
And I know, I guess the point is, okay, if you're wrong, it's one step, so to speak. You can always go back or whatever. But when it evaluates further, that could be basically the point is, let's say you have a black hole, or you have something where 2 things diverge and they never come back together. Well, like locally at that moment, right before they diverge, you don't necessarily know. I mean,
I'm not sure that's I think the point here is that somehow, if the proofs get too far apart, well, I'm thinking about it axiomatically. If you've got 2 proofs that are very far apart,
I guess the question is, what do we mean by far? What's far?
in the spatial slice somehow. I'm still trying to get intuition for what on earth it could mean to say, I don't know what the mathematics usually, okay. We've got all possible axioms. What the hell is this? How does this work? How does this work? And I'm afraid we maybe get, trying to get too close to details of photons and slits and things like this.
Is the confusing aspect the analogy in physics?
Possibly. I mean, I think the question is, what is the general phenomenon? The general phenomenon is the observer, if the observer tries to conflate things that are far apart, there will be garbage in what they conflate. That's the claim. And that will be a claim of computational irreducibility, basically. That there's enough irreducible stuff bubbling around that you might be able to locally make sure that it comes from some consistent source.
Yes, right.
But further out, you can't guarantee that. So in other words, if it's so, okay, so the claim is if things stay sufficiently close, the computational irreducibility from the environment won't affect you. And you will see things without noise, and you can see things without noise. But if it gets too far apart, all you'll see is noise.
I guess still, what troubles me is if you take this example of AAA and BAABA, okay, those are pretty close, and it's only 2 iterations. You can go back and you can start to ask, okay, what rule yields this result? Okay, fine. You can cut and look, and you didn't have to go back that far, and they're close together. So even a bounded computational observer can find that rule. Okay,
Yeah.
but then the other question is, and this is where Judea might even poke his head up, which is there are counterfactuals, which is what if, can I come up with some other circumstance in which I get these two, but it's not the same rule? But they're 2 different rules that give 2 different results, so to speak. So this is what troubles me, is maybe you can find some reason to think that it's part of the same rule, it's going to give the same result. But what if you also find evidence that it won't, even though they're near each other?
Thinking. I still want to come back to the intuition here. The intuition is what's the intuition in space? If you get 2 effects, okay, so you start from some point, you've got some event, and you've got 2 different events that are the result of that.
Yes.
If that original event led to just basically one nearby event,
Yes.
it feels more like a non-shredded space story.
Sure. That's fine.
If the event ends up with 2 little ripples far apart, that's not convincing. So 2 ripples far apart in physical space, that's not that's not persistent propagation of an observer. That's an observer at one point has split into multiple micro observers.
Yes. Or if you tried to conflate too much that's far apart, wouldn't everything just become gray?
Yeah, I think so.
Yeah.
Okay, so what is the analog of that in mathematics? What does it look like if in the entailment fabric,
Mhm.
if you are lost. Sorry, just a second. Sorry.
In some sense, to Nick's kind of bridging off what Nick was saying before, so before we've thought of what we've called rule viruses, which is some two-way rule where if you take that as an axiom, you're going to be in trouble, right? And this is just some two-way rule. But there are kind of higher versions of this where it's not a two-way rule, going back and forth, but it's some back and forth between whole paths. But it's similar in the sense that if you take that equivalence, kind of building off what Nick was saying, at that higher level, you also have this damaging effect. Like if you had some absurd axiom as the germ of your entailment cone, it's some higher level generator of absurdity, right? It's not something it's not just some axiom that you entail from. It's that now you have paths, and if you take wrong, equivalences between these paths that aren't equivalent, it's like some higher virus. So
right. Well, that's saying. You're saying if the observer conflates things that shouldn't be conflated,
yeah,
then the observer will conclude things. We'll just have a principle of explosion, so to speak.
Yeah, right.
Yeah, that's what I'm saying. It's what I think we're all saying the same thing. I mean,
definitely.
If the observer,
yeah.
If the observer, right. You're saying if the observer adds too many completions,
yeah,
they'll get explosion.
Right. Yeah.
Okay. Which is the same thing. Let's see.
I don't believe it.
What? Nick, this is like a homage to what you were just saying. Homage.
Not really. I don't know. It's just I don't think observer is capable of adding completions that's gonna explode. Like the whole point of observing is actually is to add only valid completions.
I know,
That's
but what do you mean only valid completions? I mean,
those completions that actually true in a way, right?
well, they're true in the sense that they come from branches. Like here, we could do a completion between this and this.
Yeah.
I think we should
then
try
using
it.
Using this completion, you can add a completion with another rule, and you can do it iteratively.
I get it. But I mean, I think, look, what does it mean to explode? It means that you can get to everything. So the question is.
And by the way, observers, like, okay, physically, it becomes something hard to imagine. But mathematically, it's very real. I mean, basically, it's kind of funny. In the end, when we say, you get shredded as a mathematical observer, in practice, what it means is you do math incorrectly. And as I'm sure you know, that's definitely possible. People do it. It's something that can happen. In physics, it's one thing. Imagine yourself getting shredded is, science fiction. But admitting something that's absurd into your entailment cone and then, proceeding along those lines and getting wrong results. I mean, people do that all the time. People
that's material implication with falsity.
Yeah.
Once you have something false, you can conclude everything.
Yeah, but the point is that in physics, it's hard to imagine it happening physically. In mathematics, it happens all the time. People work really hard so that it doesn't happen. It's not some analogous thing like, you can get shredded as an observer in mathematics.
So you're saying physical observer is not the same as mathematical observer. They kind of do different things. Physical observer
Yeah.
is like constrained to the actual universe and some set of axioms, but the mathematical observer doesn't have this constraint.
Yeah, that's why I mentioned this article Stephen wrote in 1984 for Scientific American. That's basically what he says, which is with experimental mathematics with computers, you can explore basically what you can't do as a physical observer. This is more or less what Stephen says in like the first few paragraphs. So that's why I'm kind of confidently recapitulating it, because this is an old idea.
Well, and I think one of the other problems is that experimental mathematics is different from traditional mathematics. Where experimental mathematics can go is different. And ruleology is different from traditional mathematics. It can go off in
Well, definitely, because it's starting at the EAM level.
yeah.
The base is different than the base of, say, the metamath language. It's like we're kind of compiling what they kind of refuse to do in metamath. And maybe for good reason, because once you get down to that level, it's, well, there are all kinds of EAMs. Not all of them have a place in human metamathematical practice.
Well, it doesn't stay together, but I'm still trying to understand, what does it look like when you have too large a region that you are conflating in metamathematical space? The basic claim is that as soon as you have a large region, you are entraining things that are just pure garbage from the sort of axiomatic background. In other words, there's an axiomatic background, and while you're in a local region, you can, it's almost as if there's this kind of axiomatic background streaming through the system. But if you're looking only at a local region, then the chances are that the edges you're looking at will just come from one axiom system.
Right, because the syntactic distance is probably not that great locally, so that you can crawl some centimeter, not really a centimeter, but you can go some short distance syntactically. And unless it's probably not the case that semantically it's catastrophic, unless there's some avalanche. This is actually in cryptography, like the avalanche criterion, right? It's actually an interesting example where you go some small difference syntactically, you change something by some small amount, and semantically it's totally different. You've actually managed to get in trouble very quickly.
Well, but in this case here, if we've got something coming from a completely different axiom.
Yes. Okay.
Then the fact is it's going to give different strings most of the time.
Yeah, definitely.
But if you have an observer region that is big compared to those, then you'll see both the strings from both of those sides, both of those pieces.
Yes.
And then the strings that you'll get out are, so I mean, okay, if we could lay this out, let's say we laid it out just according to the string names.
Okay.
I mean, I suppose an analogy to this would be a numerical multi-way system, two numerical multi-way systems. Okay, so here let's do that for a second. Okay, so here we've got one numerical multi-way system. And now what we want to do is we want to get another numerical multi-way system, like let's say 2n plus 1 and 3n, let's say. Okay, there we go. And now what we want to do is we want to say graph union of these two things. That was pretty incomprehensible. But you see my point. My point is that somehow if we're at 4, okay?
Yeah.
If we're at 4, then we only go to, okay, let's say that we have our equivalence class is 4 and 3. Maybe a bad example.
Yeah, they both go to 7. Because 7
Yeah, I understand.
share.
I understand.
Yeah.
But what I'm saying is, let's take something which was only in
10,
4 and 6.
4.
4 and
Yeah.
6. 4 and 6 are just in that left cone. Okay.
Yep.
So with only 4 and 6, things should be okay. And we should only get to
the entailments of the first.
Yeah.
Well, yeah. I suppose they're pair.
Actually, a good way to do this might be with strings, right? Where we're looking at.
But wait, let's take with this example. So let's take another one where you might be in trouble.
Oh, 4 and 3.
Okay. Okay.
4 and 3, we can now get anywhere.
Yeah, I mean, you still get the 7. It's kind of reassuring, at first, but ultimately, you're probably going to be in trouble.
You can get to anything. Whereas with 4 and 6, we can stay localized on the left, whatever, for a while. That's the claim.
I guess my only question is, can you explain how we get anywhere? Do you mean just anywhere in this graph? Or you basically mean if 4 equals 3? Do you mean 4 is 4 equal to 3?
4 equal to 3.
Oh, then you're
equal
doomed.
to 3.
Yeah.
Then you will be able to derive. You'll be able to derive equivalences.
Yeah, between
lots of things that, but perhaps there's a better example in which we have strings.
Okay. In
which both of these are from strings. Okay, where this one is giving some. How should we do this? I'm feeling like it should be like an A, B, and C, and they only. Oh, I don't know. Nick, does this make any sense to you, what we're talking about here?
A little. I don't think what does it mean? Like you have 4 and 3, they are from different multivariate graphs, so they will produce from different axioms. So how can one observer living in one of them even see a 3 in order to conflate it? Because 3 doesn't exist for him.
No, but the whole point is in the Roolead, all axiom systems, you start from all possible axiom systems. And so the whole point is that what we're saying is the mathematical observer is what determines which axiom system are you using. And so if the mathematical observer can basically localize themselves to only be able to follow through with respect to one axiom system, then all is good. But if for whatever reason the observer extends themselves to the point where they're spanning over lots of other axiom systems outputs, then they are effectively entraining all those other axiom systems, and now they will get garbage. I'm still trying to understand what that means operationally in math. So you're saying we've got these two proofs. They're making use of very different things. If
Then you
there's,
combine those,
yeah,
combine axioms from different graphs, right? In order to complete this new proof and conflate two tokens from these two different axiom systems.
What I was trying to
Then
say
what?
before is it's like you have your rules, okay, fine. And if you follow those individual rules, so let's say you have some, okay, yeah, okay, that's fine. We understand that. But then it's like if you take them to be equivalent, it's like a rule between the rules. And that
Yes.
rule between rules might be absurd.
sure, it might be absurd.
So
But
that's the point. You can't always just take, a rule between any two given pairs of rules, just like not all axiom systems yield useful mathematics.
well, hold on. That's what you're saying. In an accumulative system, the rule between rules will be an equivalence between, be saying that two of these equivalences are equivalent. I'm fairly confused here. No, I mean, I think the big picture is roughly right. That if you are pulled too far apart, somehow in mathematical space, if the observer is trying to sort of consider simultaneously valid these things that are too far apart.
So here's another question.
Yeah.
Like, is there like an example when you have two axiom systems that are consistent separately on each other, right? But if you combine two axioms from those axiom systems together, like complete and derive a new axiom using those, can this introduce an inconsistency?
Okay, that's a good question. Can consistency plus consistency goes to question mark? Can two consistent axiom systems get combined to yield inconsistency?
So what about going back to what I was saying before? So, we know, for instance, if you have X two-way rule Y, and you take that entailment code, you're going to be in trouble, right? Okay, now what if you have X two-way X as one? Well, that's perfectly fine. And you have Y two-way Y, well, that's perfectly fine. But what if you take the rule between those? X two-way X, two-way rule Y two-way Y. I can't see how that would be okay. It's like absurdity, but just one level up, where it's a rule between rules that's also absurd.
Nick, in your para substitution, for example, can you get from X goes to X, Y goes to Y? Can you derive X goes to Y from that? Oh, no, I see. We're not deriving it. That's the whole point. We're combining these rules.
Yeah.
What's the difference? Oh, combine them and
We're
derive.
forcibly combining them. We're just saying the observer is combining these. It is a meta outside the system combination.
I mean,
Combining
technically, it's
output.
also in the Roolead. I mean, rules between rules are rules in the Roolead, so to speak.
Yes.
So it's there, so you can observe it. It's something that can be observed in principle, but if it's false, then you want to exclude it.
Well, okay, but I mean, so you do that. And we've introduced these two things. We've somehow combined them. I'm still trying to get an intuition here. We've got these two very different proofs. We think in the end, well, the two, let's just take the expression thing. There are two things that are both equal to the original thing, but they're getting further and further apart. And now we say, understanding this. Well, we're saying it's a property of the observer that they will conflate everything in this whole swath of stuff. It's a meta property of the observer, not derivable from these underlying rules. The observer, by the time the observer is the observer is picking up sort of a convex hull of things within that region.
Mhm.
Just because that's what observers do, let's say.
That's what observers do, right? But it could be done poorly.
Well, right, but as soon as you do that, then all that stuff in the middle that you also picked up will run off in all kinds of different directions. So why is the mathematical observer doing this picking up of everything that is syntactically similar?
Because the results can be, when it's done right, it's because the results of the proof, the end result, can be semantically deemed equivalent.
Oh, I think the reason is because they didn't use a proof assistant program. In other words, they are effectively conflating those things.
I agree. Yeah, I agree with that. That's right. So basically, to put our two responses together, they can just look at the end result of, say, different proofs. They don't actually care about the details of the proof itself. They can forget about that and just say, look, I get the same result both times. But if they actually delve into the machine level, all of a sudden proofs differ, there's destructive interference, and syntactically you realize that they're not the same at all.
Right. But so what we're saying is they somehow conflate things, and if they've conflated two things, they've got part way in a proof. They've got things far apart. Now they say, I'm going to conflate them. Well, okay, first thing is, if they conflate over too large a region, they'll entrain stuff that is essentially noise. Now the question is, it could be true oh my gosh, this is confusing. This is really confusing. Basic claim is, you see, this thing about treating as equivalent, things that are really very different.
Yes.
What is a practical version of that in mathematics?
Well, wait, different how? You mean the proofs that arrive at them are different? You still treat them to be the same?
Yeah, I think so. In other words, I think, let's say you've got an algebra path, you've got a geometry path for proving something. Okay, and now suddenly in the middle, you say all geometry and all algebra are the same somehow.
It might not have to be that complicated. It could be some simple proof. And you just imagine you take different steps to get there. But in the middle, if you didn't know the end result, you would have no reason to say that those are the same.
Yeah, sure. But what does that mean? Oh, I see what you're saying. You're saying in the middle, you don't have a reason to say they're the same. But so what? What is that? Why is that the analog? I'm confused. I think there's a different phenomenon. There's some phenomenon here that if the mathematical observer tries to conflate two different proof paths, something not right here. The real question is, what type of phenomenon, what type of thing is this going to be? The type of thing is going to be shredding, it's turned into noise, whatever, any of the above. That's what it really is that destructive interference has to be the proof paths are far enough apart somehow.
Yes.
That I'm really confused here.
Oh, wait. Oh, Nick, were you going to say something? Stephen, does it have to do with, okay, so they're so far apart that if you were to consider them equivalent, I mean, how does irreducibility or the distance or the amount of computation involved in trying to connect them, does this come in? Is this
maybe
trying to think about what does it mean for them to be? I guess I'm struggling to understand. I mean, we've kind of danced around this quite a bit, but there's some additional aspect that you want to find still. And I guess I'm not exactly sure what that is.
Well, I think what I'd like to find is this idea. It's really destructive interference. This idea that two different proof paths wind up at different ends of metamathematical space. But I still want to know, what does that mean? What does that mean in observing? And that means that the typical observer, okay, what happens with the photons is two slits is worse than one.
Yeah.
Okay.
Yeah.
So and that's kind of the slogan. So if that's the case, what is the analog here? It's like two proofs are worse than one. Well, that's what we think the analog is. Two distant proofs.
Well, what I was trying to say before is if you have, let's say you have a dozen proofs, and maybe they diverge and they're quite distant at some point, okay, but you've run them to completion and you see that they yield the same result in the end. Well, then in that case, it's a very nice result, which is this theorem has a high proof density, and you can see that there's this whole kind of swath of metamathematical space that is in some way equivalent in that it yields the same result. So it's fine when it actually yields something that's common, and that's where proof density comes in. But in the absence of something like that, it's like entropy. I mean, it can go in all these different directions, and especially if you're observing it and it's hasn't completed running, it could very well not yield the same result. And if you view them as equivalent in the middle, before there's any real semantic understanding of what theorems they prove, then it's going to be at risk of yielding all kinds of absurdity. I guess the key question here is, I'm thinking of semantics as something that kind of happens at the end after this thing has run its course. And I guess I'm thinking about finite proofs here. And that's why, for me, it seems kind of natural to think about destructive interference as just something isn't done running. And if a multi-computation isn't done running yet, then there's destructive interference. And it's like this uncertainty that arises both because of multiple threads of time and also because of computational irreducibility. When you put those two together and you're running something, then there is, of course, this risk. There's this interference effect.
Okay, explain that again. I don't know.
Okay, So computational irreducibility, I don't need to explain. Multi-computation, you have multiple threads of time. And if something is running, and if you don't know what the rule is, you just are like, you've walked into some room and there's some multi-computation that's running, and someone asks you, that blue path, that red path, that green path, you can see that they're diverting. Someone asks you, okay, do you think that it's going to yield the same result? You have no idea, because one, of irreducibility, you have to wait and see, and two, because of multi-computational parallel evaluation, you can actually see the irreducible computation that's multiple, and you really don't know. Not only do you not know what the end result's going to be, which is typical irreducibility, but multi-computational irreducibility is not only do you not know what they're going to do, you don't know what they're going to do with respect to one another. And if you're thinking semantically, if you're thinking of semantics as the end result, and how can you in this case think about clouds and equivalences and how these different proofs give the same results, you don't know. And so I'm viewing,
Don't know what.
you don't know if the two paths are equivalent, that they yield the same result. That's kind of multi-computational irreducibility at work there, this destructive interference.
Well, okay, try that one more time. You don't know that the two paths, which are tangling around each other.
Yeah. You don't know if they're going to yield the same result in the end. Just like with typical computational irreducibility,
Yeah, no, I
you
understand.
don't know what you're going to get.
So
And
you're saying,
yeah,
you're saying multi-computational irreducibility.
yeah,
Okay, you're saying that is not only do you have to run a single thread and see what it does,
yes,
you have to run all the threads.
yes,
To find out, e.g., if they do the same thing.
that's right.
Okay. Well, that's interesting, but how does this relate to destructive interference?
So destructive interference is necessarily an effect on the observer due to multi-computational irreducibility. It's this uncertainty regarding the equivalence of the paths, because you don't know, because it's irreducible. And when you're trying to look at the relationships between the paths, because it's irreducible, you're uncertain about their equivalence. And so that is destructive interference.
Why?
It's so if destructive interference means that you have, okay, so as I understand it, right? Let's say you have two paths and they actually yield the same result. Okay, in the end, they yield the same result. But if you look kind of midway through, they're quite different syntactically, right? Okay, so what that means is, now when you think about the actual computation running, what it means is you have a number of these different computational evaluation fronts, and that their behavior is different with respect to one another. Okay, so standard computational irreducibility tells you have to wait and see in order to know how it behaves. And the multi-computational wrinkle here is, not only, as you just wrote, not only do you not know what's going to happen for each of them, because you don't know what's going to happen with each of them, you are uncertain about the
Right,
relationship of the
particular,
results.
does it wind up getting somehow far apart? Do these
Yeah.
threads?
Yeah. You don't know what the ultimate distance will be of their outputs. Let's put it that way. It's more simple. You don't know how far apart their end results are going to be. It could be the same thing.
So what does that mean in practice in mathematics?
What it means in our framework, at least, especially if you're starting from the EAM level, is that in a basic sense, one thing that we've been saying is that you can prove perhaps you can prove theorems in different ways. Okay, this is the first thing, first important thing. Multiple proofs for some theorem, which means it's even an intelligent question to ask, for some given pairs of evaluation fronts, different paths, are they ultimately going to contribute towards some cloud or not? And after waiting for some irreducible computation, you can say, but during the computation, due to computational irreducibility, there will be this interference effect because you'll have these different paths that are syntactically quite different. And you won't know until the computation completes whether or not these seemingly syntactically dissimilar evaluation fronts are ultimately yield some result that's semantically equivalent, or if they end up yielding results that are far aflung from one another in metamathematical space.
So what?
I don't know. I'm sorry,
okay.
I don't know so much, but this is what we've been discussing.
No, I know, but I mean, what this is saying is an observer who believes that in the Roolead that their things are operating according to a particular axiom system.
Okay.
The difficulty is going to be that these two proofs get far enough apart that somehow they can no longer believe in a single axiom system. Right?
Okay.
So the claim is
fine. Yeah.
Right. Okay, two proofs can get far enough apart in metamathematical space that an observer won't believe or won't believe they come from the same axiom system.
Yeah, I understand. Shouldn't. I mean, that kind of makes sense too.
Right, shouldn't believe that they come from the same axiom system.
It's, it reminds me of economics in some sense, where we have this idea of like a rational, mathematical observer who's making good choices, so to speak. Not everyone will make these right choices, but it's helpful to think
believe
about.
That they come from the same axiom system.
Right.
Because if they do, they somehow entrain, if they do believe it, because if they do believe it, they wind up believing in some intermediate cases that correspond to different and quotes wrong axiom systems.
Yeah.
Okay, so let's take the case of you've got a geometry proof and you've got an algebra proof.
Can we just do some concrete example?
Well, I'm thinking about it at the level of sophisticated math. So let's say you've got a proof of some result about circles that's being done in algebra and in geometry.
Great. Okay. Good. Okay, good.
Now, so we've got an intermediate stage of each of those proofs. One of them will be stated in terms of all kinds of geometric things with angles, and another will be stated in terms of polynomials.
Yes.
Okay. So now, what the hell goes wrong?
Yeah, I mean, sometimes it won't go wrong, right? Like if you have,
but let's say it does. Let's say it does go wrong. Okay, so we say, two branches, one geometry, one algebra. Okay, so now at an intermediate stage of the proof. Okay, we've got a translator at the beginning and end. The beginning and end of the proof Oh, I think I see what's going to happen. I think I see what's going to happen. The beginning and end of the proof, we have a comparatively fast-running translator.
Aha! I see where this is going. I see where this, yes, go on. This is, now we're getting at motion.
Yeah, right. We have a
Yes.
comparatively fast-running
Yes.
translator between the geometry and the algebra.
Great. Great.
Okay.
Great.
In the middle, they're a big mess. And it's non-trivial to do the translation. So we can see that explicitly, probably.
Yes. Yes.
Because it's no longer, and in fact, you almost probably have to go right back to the beginning on each side to get the translation done.
Fine.
So okay, and in other words, the question probably the answer is that to do the translation, you have to break the thing down into atoms, right? To do the translation,
Yes.
you can't do it at a high level.
Yep.
You have to break everything into atoms.
So what if the translation distance exceeds what a computationally bounded observer can do?
Yeah.
Right?
Yeah.
Right.
But then what would be the significance of that? What would they conclude?
Well, they wouldn't be able to confirm. They wouldn't be able to translate between the two of them. So what would they conclude? Well, they can either say that they're equivalent without having actually translated between them.
In which case they run the risk of having garbage.
Right. So they haven't vetted it. Right. Or they say, okay, I'm not going to say that these two are equivalent because
I see.
no
The point is, okay, if they do say they're equivalent.
Yeah, it's non-constructive in some sense because you don't actually have a translation between the two.
Right. If they do say they're equivalent, they're making a leap of faith.
That's right. That's right.
Because they can't verify it.
That's right.
They can't verify it at that moment.
That's right. That's right. They're doing math like Kierkegaard would.
I don't know what that.
A leap of faith was one of Kierkegaard's kind of concepts.
Okay, but they can't verify it at that moment. And so that means, what does it mean? It means that, yeah, whatever they're doing to make that leap of faith, they might make that leap into all kinds of other places because they can't actually tell what's going on.
Yeah, and in some sense, I mean, it's like we think of, in some sense, this fourth paradigm it kind of goes beyond constructive mathematics because we're saying, well, all the rules are in the ruleyat, so to speak, right? So I guess technically everything's constructive, but you have to decide what you're going to observe. But in this case, if there's no translator between these, I mean, now all of a sudden you're, as an observer, making conclusions based on something you haven't even observed in the ruleyat. I mean, you've observed these two paths, but you haven't observed the translator between the two of them. So like you don't have any observational basis. You haven't observed the constructor at all.
Right, right. So you're the leap of faith. In the leap of faith,
yes,
you have no constructive path.
That's right. That's right.
Okay, so let's just review this again for a second. So what we're saying is, at the beginning, it's straightforward to do the translation. They're very close.
Yeah.
Later on, they get quite far apart, and the only way to do the translation becomes very difficult to do the translation in practice.
Right. It might exceed, and it might exceed what a bounded observer can even do.
Yes.
Yes.
And therefore, okay, what's a practical case where people have done this, where you make a leap of faith? Well, Grothendieck was trying to make a leap of faith in his hypothesis.
Conjectures. I mean, all conjectures are leaps of faith. But there are conjectures, even like the Langland's conjectures, where you're basically saying you will have some analytic and some arithmetic. Those two things they're gonna link up in some way.
Jumping conjectures.
Yeah.
E.g., Langland's, Grothendieck, etc. But now we believe that these conjectures are correct. But what would it mean if we made a jumping conjecture?
Yeah. Well, it would be like
Generally,
having,
yeah.
Well, it would be like in math having, some discredited theory in science, where people do all this mathematics with some belief that some conjecture holds. And they might even say, this is presuming if this is true.
Okay, what's an example in math? Okay, so fine. This is, so let's say that, okay, so this is a case where assume, I mean, unfortunately, this is a fairly specific kind of conjecture that we're saying might hold between two different proof branches. Well, it's not necessarily between proof branches because they didn't necessarily know where it came from. Okay, assume there is a conjecture, but it's bad. Okay, what's an example of when that's happened in math?
Oh, where something's been proved to be
false.
false.
I know an example. It's the prime number theorem. What is it? The thing these various Ramanujan related things.
Oh, okay. I'm not sure.
E.g., prime pi is greater than whatever it is.
Okay, there's a wiki page for disproved conjectures.
Okay.
Hold on. Oof, von Neumann conjecture. Oh no.
Disproved mathematical conjectures. Okay.
Polya conjecture. Huh.
Oh, actually, there are probably some of these differentiable functions and so on that end up being okay, let's take the very basic one, the Pythagorean claim that all numbers can be expressed as rational numbers.
Okay.
Okay, so e.g., the Pythagorean claim, all numbers are ratios of rational numbers, ratios of integers. Okay, so then how does that fit into what we're talking about? Well, you can prove all kinds of things. I see. So then maybe what happens here Okay, in this case, e.g.,
Mm.
one branch is about numbers represented symbolically, let's say.
Okay.
One branch is about P over Q numbers. That's still not right. Still not. Oh, yeah. I see what's going to happen. Okay. Look. We are really talking about. Yeah, we're really talking about rationals. But we have general
Right.
statements.
Right.
We have general statements about numbers. So let's do an example. So let's say we're making a statement that x plus y. What's a good example? I have no idea. Let's say x plus y over 2 is greater than the arithmetic mean, square root of xy. I forget, is that the right way around or the wrong way around? I can't remember. Let's say it's that one. Okay.
Okay.
And we have a way of proving that purely symbolically for arbitrary x and y.
Okay.
And then we have a way of saying that is P1 over Q1 plus P2 over Q2 is greater than whatever.
Okay.
Where those are integers. And then we have a separate proof path for that. And the claim would be what the hell? If you try and somehow make those let's see, where's the list of disproved conjectures? Yeah, I mean the most famous, by the way, disproved conjecture is is the whole most famous is Hilbert's decision problem. In other words, that all mathematics can be done mechanically.
Right. Right.
My gosh, there's a paper this recently.
Hey Nick, are you awake, by the way?
We should let him go to sleep.
Yeah, still
Yeah.
awake.
I think you should go to sleep.
Hey, Nick, it's
And we
like
should.
nine.
I think we're going to wrap up, so you're not going to miss anything here.
Yeah, I mean the next winter school lecture begins in 8 hours.
Okay.
Yeah.
Time to wrap up. We can, James, we could chat for another few minutes, but let's.
Yeah, I have something to ask you. I can chat for
Okay.
a few more minutes.
Okay. All right. Okay.
I'll go.
Okay.
Yeah.
Thanks.
Good night,
See you,
Nick. Thanks.
Bye bye.